All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and these students. Just ask you to bless our work today. Help us to glorify you what we do and to just understand what we need to before the test tomorrow, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me just talk about the math battle a bit, since that's most fresh. So the way I thought about problem one was, first of all, this one is the only vector field that has, it's going up in like by 1 unit across the board, right? And so it's like uniform in the way it's pointing up. This one doesn't do that. That one doesn't do that. That has to be this one. And also then double checking, not only does it uniformly going up 1 unit according to the scale that's chosen, this y, it points right for positive y and it points left for negative y. See that? It's pointing this way up here, it's pointing that way down there, so it's got to be that. This is not pictured. That's just the field that radially points outward, which is not that. That's the one's radially pointing inward. This is clearly that. And that one we've actually essentially done in class, but we had it rescaled by division by x squared plus y squared. That's the one that encircles the origin. It's that one. Are they conservative? Well, you can pretty easily see that 1/2 x squared plus y squared has that as its gradient. Minus 1/2 x squared plus y squared has that as its gradient. So yeah, the middle two are conservative and the outer two are not, because if you take the curl of those, or if you just check the, the thing that we integrate the area of for the Green's theorem, you know what I'm talking about? You better know what I'm talking about. Good grief. I certainly hope you know what I'm talking about. Green's theorem. Golly. Integral of p dx plus q dy, right? Over the region is equal to, boundary of the region is equal to the double integral over the region of partial q, partial x minus partial p, partial y, right? So that being 0 is a test for it being locally conservative in the plane if we're looking at the vector field PQ. So here, if I look at, P is equal to y and Q is equal to 1, and I look at that, I get minus 1, which is not equal to 0. Therefore, this one's not locally conservative. It's not locally conservative. It's certainly not globally conservative. And likewise, this one over here, if you look at the thing that goes into Green's theorem, you don't get 0. So it is not. I think you get 2. Yeah. So, yeah, neither. The outside ones are not conservative. Any questions? You can buzz in anytime you want. I don't have this all written by hand. I ran out of awakenedness after the first page, unfortunately. But I do have the typed solution for the rest of it, modulo the last problem or two. Anyway, so any questions about this? Did I calculate? I was kind of sleepy when I did this calculation. Did I get it right?
On number 3, the third one, the xy cosine, I have yz cosine.
Y. In this one?
Yeah.
This here, should that be y? We have a vote for yz cosine. Yes, that should be yz cosine. Thank you. Because this should differentiate, when I take the x inside, I should pull a z out, which would give me yz. Like I said, I'm a little suspicious of this. So, all right, so I lose a point there. All right, I don't know, it's 6 points. Maybe that's half a point. There are like 6 independent things here, right? Dunk, 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 dunk. Or do I count it as 4? Is it 4 things or is it 6 things?
Well, that should be 5z to the 4.
Dang it, what? Let's not look at this anymore. I won't be posting this. Anyway, I mostly wanted to put this up because I wanted to talk through the, the picture at the top. And in my brother's solutions, just kind of a wall of text, which I have trouble presenting. Anyway, so Problem 4, I'm pretty sure I got right, or I got wrong the same way twice. So it's probably right. But so does this help in terms of communication? If I say if I just say calculate the line integral and I don't attach any further instruction, if it's conservative, you've got choices, right? You can either do the line integral in the style of part B, or you could do, use the FTC like part A, which would be the smart way to do it. Now, that's only true in as much as I give you a curve which you can parameterize, right? If I give you an arbitrary curve where you don't really have, the specific details of what the curve is, then you almost have to do it part A, the part A way, right? However, if it is conservative and you don't have the curve and you just parameterize the line segment from the initial point to the ending point and you calculate the work done with the circulation of the vector field along that line segment, you're also still going to get the same thing you'd get from the FTC. So, although I'd still take off a point if you did that, unless you said on the side somewhere, I can do this because it's conservative, and so it doesn't matter which path I use, so I can use the linear path even though it wasn't given, something like that. Not all those words, but some of them at least. But then I would ask myself the question, why on earth didn't you just find the potential and use it? Because it's like way easier to do that, So anyway. All right, let me flip back to my brother's solution here. Actually, I'm going to go back to this one. Let me just talk about the last page. I won't write. I'll just explain. So let's see here. Let's see here. So I'm going to steal one of your answers. Or you'll tell me. If you could guess it yesterday, you can guess it today, right? What was the answer? Or a answer. There's actually infinitely many, right? For like the finding the G and the B. So F, here's the way I think of it, guys. I look at the vector field, all right? And I look at it and I say, aha, part of that is clearly conservative, right? The part which points in the direction of the components, the conservative piece, essentially. It doesn't have to be exactly that, but if you do just have pieces which are x and the x, y and the y, z and the z, you can just separately integrate them. That's like sort of stupidest possible kind of conservative case. Of course, you could also have things that are like balanced, like you could have an x squared. You could have like a, let's see here, an xy squared in the x component paired with a yx squared in the y component. Those would both be coming from the basic 1/2 x squared y squared. So you could have terms like that are straddling components, but that's not even necessary here because I can just peel off x squared y cubed z to the 4th. Did I say x cubed? No, x squared. Y cubed z to the 4th. That's my first piece. And then the other piece is got the variability in the opposite coordinate. And whenever you have like variability in the opposite coordinate, which isn't somehow like balanced by other opposing terms, that's going to give you a non-trivial curl. All right, and the piece that has a non-trivial curl cannot possibly be the gradient of a potential function because we have the curl of a gradient 0, right? So essentially, I thought about this in constructing the problem, and I knew that you'd be able to find the gradient of something here. In fact, it's just what? 1/3 x cubed, 1/4 y to the 4th, plus 1/5 z to the 5th. I can integrate today, right? I couldn't differentiate yesterday, but there you go. So that's a good choice for G, right? We can make G that. And so I can just think about the other part separately. So I want this to be the curl of something, right? And what should I put there for that? What'd you guys find? I don't want to eat 10 minutes of class guessing. It takes me a while to work these out.
Minus 1/2 b squared. And I think it was 1/2 x squared
I think that's, yeah, I think that's what you showed me. But this is a great, let's check, right? Let's calculate the curl of, and I'm just gonna, I'm gonna forego the halves. Oh, will I keep the half? I guess I'll keep the half. So minus z squared over 2, x squared over 2, y squared over 2, like there's a minus y squared over 2, yeah? So a not unusual first question on my test 4 is like, here's a vector field, calculate its gradient and divergence. That's a gift, right? In the world of setting up line and surface integrals, the problem of just calculating a curl and a divergence, I view that as a gift, you know? So I'll write it out this way. So we've got partial x, partial y, partial z, and they're acting on this vector field. And so I've got like x hat, partial y minus y squared over 2, minus partial z, x squared over 2, minus y hat, partial x, minus y squared over 2. Could save myself a lot of time by not writing down all the stuff that's 0 here, but I'm just going to do it. All right, and then z hat, partial x, x squared over 2, minus partial y, minus z squared over 2. Okay, so a lot of this stuff is 0. But what do we get? The thing is, if we get the wrong thing, we can kind of easily see how to adjust the answer, right? But I think this is what Shane showed me yesterday, which we checked. Well, he said he checked yesterday, so I trust him. But this gives me a minus 2y, right? So I've got minus 2y x hat, but that 2 over 2 gives me just minus y. And then this one, that's 0. This is minus minus gives me plus, so I get a z there. Oh, wait a minute, but there's 3 minuses, so minus z. And then what? X, right? Now, is that what I wanted? Huh. So let's see here. The minus y is what I wanted. But the z and the x need to flip-flop, right? So apparently we remembered it wrong. What should we have done? So you can see from this calculation what we should have, we should put b equal to, so thinking a little bit, we have b is, we like the y where it is, we want to flip the, so we got z squared over 2, and as Shane said, it might be off a sign, and I think he was right. So see if I flip the minus on the x and the y, that should make this become a plus y. Okay, I flipped the sign on the z rather. I'm too close to it. Am I right, guys? Okay. My mind keeps flipping back and forth between what I'm thinking about and what I was checking. So I'm pretty sure that gives you a curl that gives you the other piece, right? Now, how did you find that? You guessed. Excellent. I think that's the way to do these. Now, you can systematically, like, you can pick one component and make the one component work, right? And then you can kind of like go from there, building off an initial guess. You can build your guess in stages with the understanding that you have to hold on loosely. Don't let go. If you cling too tightly, you might lose control. But you know, you do one thing at a time, and then you'll get all the way through. But anyway, so there's that. Now, what's the point of all that? The flux through the surface of the volume. So let's see here. So thinking about that, through the surface of the volume, let me call the volume, I'm going to call that volume E. So the flux through the surface we can do as what? The divergence theorem, right? Or the boundary of the cube of the divergence of F, right? But what's the divergence of a curl? Zero. So the B part of the vector field contributes nothing to this one, and you're just left with like the integral over the. What's wrong with me? Look at this. Seriously, is this the way divergence theorem works? Don't let me do this. Come on, guys. This is what? Exactly backwards, right? The boundary has to go over here. The solid has to go over there, right? You can think of it kind of as, in some sense, you can think of Stokes' theorem as trading a derivative of the boundary for a derivative of the integrand. You can look at it in that sense, right? Like, in some sense, you're moving this derivative over to that derivative. And that might partly answer the question why we use the partial notation for the boundary. It's partly for that formal analogy. There's deeper things to say about that than that, but okay, so what is the divergence of F? Well, it's nothing more than the Laplacian of the potential part of F, the G. Because the curl piece vanishes, so all you have to do is look at your G and like calculate, you know, the Laplacian of that, which is what? Take two derivatives, right? Like this nabla nabla, nabla dot nabla is nothing more than like partial squared x, partial squared y plus partial squared z acting on G. That's what that is. And so if you calculate that there, you get, what happens when we twice differentiate this with respect to x? We get what? The 3x squared. We get a 6x, I believe. And we get a, what? For, is it 3y squared? The one is just 2x? Oh, yes, I'm sorry. So 6 over 3 is 2. I'm a dummy. 4 times 3 is 12. 12 divided by 4 is 3, so plus 3y squared. And differentiating z twice, 5 times 4 is 20. 20 divided by 5, so we get 4z cubed. And then you got your, dx, dy, dz. And all of these bounds are nice and simple. And so you can do that integral, right? What's it work out to? It works out to 1 plus 1, well, yeah, 1 plus 1 plus 1, I think. Did you guys get 3? I could be wrong about that. I'm probably wrong about that. Let me just, anyway, you can work it out. I don't really trust myself on that. I do know that you guys can do this integral, though, right? Well, I hope. So, on the flip side, for part B, the circulation of F by Stokes' theorem will be completely governed by the B part. You're just, by Stokes' theorem, the integral around the boundary of, what did I say? The curve formed by that intersection. Let's call that curve C. All right, C is the boundary of some surface, right? Of f dot dr is equal to the double integral of the curl of f, all right, around S. But because the curl of the gradient 0, that's just going to be depending on the curl of B, right? And then you could go a couple different ways there. The one way you could, like Shane was looking back at the identity we had for the curl of the curl, which we had an identity for that I derived one day. You may or may not remember this. It should probably be on your sheet of formulas. That would be smart, right? But the other way to do this calculation is just to think where it came from, right? We know that the curl of B by construction is what? It's this, right? So we could have just gone, oh, okay, well that's, oh, wait a minute. I'd still have to take the curl of that, wouldn't I? But anyway, you could do that, right? That's actually a pretty simple one. If I remember right, it's like 1, 1 minus 1 or something like that, right? But anyway. So just I wanted to sketch how this one went. I'll try to write up the solution formally for you guys and post it, all right? Because I think I owe you that. I just don't have it done yet, so my apologies. But so I'm planning to write out the solution for this and post it for you guys. This one, you can calculate the divergence. We actually did calculate the divergence of this as 0. That was a homework problem, the first piece of it, right? And by the chain rule, the divergence of the other piece must also be 0, because it's nothing more than a linear shift of coordinates, right? So like the calculus is the same for this and that. It's just that we have x minus 1 instead of x. So if the divergence of this is 0, the divergence of that is 0, the divergence of all of this is 0, which means that the flux of this vector field through any sphere only depends on the places where it's divergent. And we've also calculated that the flux of this vector field through around a sphere which contains the origin is, well, it's 4 pi, ignoring the 2 and the 4 pi. So you'd actually get a flux of 2 from this piece. Any sphere which includes this gives you 2 for flux. Any sphere which includes this gives you a minus 3 for the flux. So the different cases are like, if you have a sphere which just includes the origin, the flux is 2. If you're including the origin and the point, see, I think I understand why you guys were talking about, is there 2 cases, is there 4 cases? I understand why now you're going to talk about that. Now, if we're thinking about the origin, if we're thinking about the sphere centered at the origin, there are only 2 cases. But if I can move the sphere, there are more cases, right? Kind of like it depends on where the sphere is centered. But my standard notation has been that this sphere is centered where? The origin, right? So if that's the case, then there are only 2 cases. There's either when you're just encircling the singularity at the origin, or when you're outside, you've encircled both of the singularities, like any radius that's big enough to pick up on this, which would be like what? The square root of 3, radius 3, right? Because that's distance 3 from the origin. 1, 2, 2 is the square root of 1 plus 2 squared plus 2 squared, which is square root of 9, which is 3. That's distance 3 from the origin, this being 0. So if the radius of the sphere centered around the origin is bigger than 3, you pick up a flux of minus 3. So for any radius larger than 3, you'd have a net flux of minus 1. Is that what you guys got? Oh well, I haven't looked at it. I thought maybe you guys got it, but if you didn't, it's all cool. There's like significant bonus credit on this math battle, right? So, all right, let us look at like mission 8. You guys can jump in if you got any. Maybe we should look at the. We could look at the old test 4 solution. What would you guys like to look at? We can. Lots of things we could look at here. Nobody? No preference? The solution to the math battle is posted. The other parts, it's just it's the the type solution that my brother wrote for you guys. Well, I guess you didn't write it for you guys, but he didn't know he was writing it for you when he wrote it. But My brother's pretty careful. There's probably not any errors in that solution. But tell you what, I'll go back and look at that old test because we maybe haven't done that together yet. If I can find it. I think it was 2015, wasn't it? 2018? What was it? Do you guys remember? The old test I posted?
I thought it was probably last year.
That would be difficult because I didn't teach this last year.
That's true.
Well, here's the one from 2018.
2015.
Oh, 2015? Okay. I hid it in plain sight. Let's see here. So here's a somewhat typical, like I said, there are any number of test 4s in this class where I start with a question which is just like, here's a vector field, calculate the curl and divergence. You know, like the pretty typical question. So as I look at this problem 1, I say, let's C be a curve from 1, 2, 3 to 5, 5, 5, right? Of course, you also need to recognize things, right? This is a line integral, right? This is the same as the line integral of f dot dr vector, where f is xy squared, comma, yx squared, comma 1, right? That is a conservative vector field. In fact, if you look at the problem here, this is what I've been telling you some of you about. If I ask a question where I say calculate a line integral over a curve, and all I do is give you the endpoints, the only way that problem makes sense is if the vector field is conservative, right? So this one is, there's its potential function, and then I use FTC and calculate. Right. Yes, this is posted in announcements. I am fond of the snow cone problem because it tests a fair amount. It tests, do you understand like how to parameterize a sphere? Do you understand how to parameterize like a cone? They're both here, right? So the infinitesimal area element for the sphere is r squared sine phi, d theta d phi. For the cone, if it's angle pi over 4, we have that. So in my notes, I have like examples 1, 2, 3, 4 for like setting up parameterizations of surfaces. That would be very smart to put on your formula sheet, right? Because you'd like to know what ds vector is without having to work it out, right? Unless the whole problem is to work it out, in which case I'll probably have language like write down a parameterization and derive the normal vector field. I would probably have that language in the problem if I was insisting on you doing it. Of course, some problems just have non-standard surfaces, so like you just have to do it because it's not one of our standard examples. Any questions about this? So let's see here. It says find the surface area, right? So this is not a flux integral. This is just calculating the integral of ds, big ds, no vector, over the surface. So there's two pieces. There's the cone and the portion of the sphere, and so I calculate them separately over the appropriate range of angles. It is important to understand the spherical angles, right? Not understanding theta and phi will stop you dead in your tracks for a number of these problems. That's true. Oh man, I was being too nice. Look at that. I told you guys this problem intends the use of the divergence theorem. I'd be in a softie this semester. What's wrong with me? Come on. What is this, kindergarten? Come on. Good grief, man. Shame. Anyway, so I'm joking. So yeah, because I was trying to protect the students against actually trying to do the integral directly, which would have been less pleasant and would have eaten an inordinate amount of time. If you have a closed surface, right, like a sphere, then the divergence theorem is a good bet. Because I trade a kind of nasty, possibly nasty surface integral for a usually somewhat tame volume integral. Now here we have to integrate cosine squared, sine cubed, but we know how to do that, so there you go. Notice that it's important to make sure that you treat dv as you ought to. If it's a spherical problem, you probably should use spherical coordinates. If you use spherical coordinates, the measure dv, remember the Jacobian brought out this rho squared sine phi, so we have to account for that in the integration, right? You don't just write down d rho, d phi, d theta. That's not how it works, right? There's like a u substitution for several variables that demands us put the Jacobian there. Oh man, I said to use Stokes' theorem. Well, that was kind. But pretty much, if you have a problem like this where you're asked to calculate, I mean, I guess, I don't know. If I didn't have used Stokes' theorem, like you could still calculate it, right? You could still calculate the line integral of the vector field around the square or rectangle, whatever it is. You'd have to do what, though? You'd have to parameterize each line segment and slog through the line integral along this piece, and then along that piece, and then along that piece, and along that piece. You have to do four separate integrals, work it out. Now, that's not impossible. And in fact, you'd have to do that if the instructions had been different, right? What another set of instructions for Stokes' theorem? If I say verify Stokes' theorem, that means that you need to do two things. You need to calculate the line integral directly, and you need to calculate the flux of the curl directly, and then you compare those two and show that they're equal. That's what it means to verify Stokes' theorem, is that you check both ingredients, the left-hand side, the right-hand side, show they match up. So verify Stokes' theorem is a lot, right? If I ask a verify the Stokes' theorem question, that's like probably 30% of the test, that one problem. It would take 20 minutes to do it, so, you know? Anyway. Ah! Nom, 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 nom. Let's see here. So here, ooh, well, I've erased it, but here we've got partial p partial y equals to partial q partial x, which is to say that the z component of the curl is 0 if we extend it to be three-dimensional, right? This is a locally conservative vector field. And it's locally conservative, except what? It's got these divergences, apparently, at the center of perhaps C1 and C2. And I tell you that the integral around the eye of Pac-Man and around his next, what do you call the things that the Pac-Man eats? No, what if he's just eating like the little dots? What are those?
Dots.
They're just called dots?
Yeah,
okay, thank you. It wasn't part of my education, but so yes, if you're using the dot, we have confirmation this is a dot, then, you know, apparently that dot, something happens to the vector field there, and it gives us a non-trivial integral around the circle C1 of 1. So anyway, long story short, the deformation theorem says that we can deform C2 out to C because they're oriented the same way, and the integral around C would be the integral around C2, and so that's why we just get 2 for the answer here. There is 1,000 different variations on this problem, but you need to understand, what you must understand carefully to be successful at this problem is the concept of orientation, right? That basically it's all based on Green's theorem, where we orient the boundary of the region in the positive sense, right? Counterclockwise for outside, clockwise for inside boundaries, all that. Oh, look, I said I would ask this somewhere. I apparently waited to problem 7. Probably because I liked the way the white space worked for the problems in this test or something stupid, but just because the problem is later in the test doesn't mean it's difficult. Sometimes I withhold the difficult problems till the end of the test, but that's not a universal constant in my testing. This one here, I'm trying to be kind conceptually for students who are paying attention, who know what time it is. You've just calculated a curl. The curl is non-zero. You know it's not conservative. You know you have no choice but to actually parameterize the line segment and work through it, like you wouldn't even try to find a potential here. And let's see here. Now I have if I say setup but do not evaluate, please do not try to evaluate. Now this one is the positively oriented ellipsoid. Now I do usually ask some question where you actually have to parameterize something. I feel like at this point in the course we've done enough things that you should have gained some understanding of how to parameterize things. And so I want to test some on that to give you kind of some recognition of the work that you've done. But a lot of times I just give parameterizations. So anyway, here, to parameterize the ellipsoid, it's basically just modified spherical coordinates, like I have up there, ABC. I calculate the normal. Once I have the normal, I take the dot product of the vector field evaluated at the parameterization, and that's the surface integral. So there it is. So if I say you don't work it out, you don't even have to take the dot product, all right? So now, see here, problem 9. Oh, look at that. Use the divergence theorem to calculate the flux through the ellipsoid. Well then, man, look at how easy. Goodness gracious, that's cool how that goes. And here we make the interesting change of variables that makes the ellipsoid into a sphere, that makes the integrals silly. So this is something you could do. You just have to use the divergence form of Green's theorem to solve this problem. All right, that's what this is. It's applying the divergence form of Green's theorem. And this one is just a plain old Green's theorem problem, but you actually have to set up the integral, type 1 or 2 or whatever, work it out. And then finally here, problem 12, the last problem is just what we were talking about at the start of class, finding a potential and a vector potential whose gradient and curl respectively give you a given vector field. I just didn't do anything with them on this test like I did in the math battle. But anyway, I'm not saying this is the test. I do vary quite a bit in the structure of tests in here. So.